Well, hello everyone. This is Mrs. Hanson. This is the last video lesson for Chapter 13 on ethers. And as a matter of fact, it's the last video lesson for Organic Chemistry, Semester 1. So we're almost there. Today's lesson is going to focus on two topics. The first of the topics comes from Section 5, Preparation of Ethers. And the last topic will come from Section 6, the Reactions of Ethers. So let's turn our focus to preparing an ether. Now remember, an ether from our lessons is the functional group where we have an ROR, where the ether linkage attaches to R groups, to alkyl groups. How do we go about making an ether? And we're going to look at two ways. One of them is much more functional. The first, to prepare simple symmetrical ethers. Symmetrical meaning that the R group is the same on both sides of the oxygen in that backbone of the molecule. And to do so, we can use an acid-catalyzed dehydration of a simple alcohol. And let's just use a model of ethanol, 2 carbons. So an acid-catalyzed dehydration of a simple alcohol, such as ethanol. Reviewing the mechanism, beginning with our 2-carbon molecule, ethanol, we look at an acid proton transfer in the first step. Notice it's the oxygen who is reaching out for the proton, and this is just the way that we are modeling an acid in solution. H3O plus represents that hydronium ion. And if we deprotonate the hydronium ion, we see that the electrons collapse back onto the oxygen, and what's generated there by removal of the proton would be water. And notice that what we've done is turned this alcohol into a better leaving group. So we've protonated the hydroxyl group so that it's ready for an SN2 nucleophilic attack. This is a second molecule of the very substance that we're trying to create. So this is the ethanol. First molecule gets protonated. Then a second molecule of the same alcohol comes in as the nucleophile. And notice here, this electrophilic carbon, which is slightly positive just based on the polarity that the electron distribution is pulling away from that carbon, making it very electrophilic, and becomes the target then of the alcohol's nucleophilic attack. So at this point, we've used 2 molecules of the original alcohol, and right here, we now have a protonated ether. We want to remove that and end up with just a straight ether linkage, and so we have to deprotonate that. And again, this is a same molecule. Here comes another molecule of the OH, and it becomes protonated, and then releasing that forms your ether linkage. So notice that a proton, right here is a proton source in the acid catalyzed. It's used in the first step, but then another proton, that's spelled, another proton is liberated in the last step. And that's just going to be able to perpetuate the SN2 reaction, needing that acid catalyst. Just remember that an acid catalyst must be used and then regenerated in the last step so that the reaction can continue. Now, this is very limited because it's only going to be able to produce symmetrical ethers because it's the same alcohol over and over again that gets used in the reaction's next step. And so the only opportunity is to create symmetrical small ethers. So let's look at a second preparation mechanism, much more practical, and it's called the Williamson ether mechanism, Williamson ether synthesis. And this is where we would tend to use over the first presentation because it works well for producing any ether. It does not have to be symmetrical. It works well for asymmetrical targets as well. And really, this mechanism lets us review 2 previous mechanisms that we've already went through earlier in our lessons. Here we have an alcohol. And here we have sodium hydride as a first reaction in this mechanism, as the first step, where the hydride functions as a base to deprotonate the alcohol. When the hydride reaches out for the hydrogen on the alcohol, we call that deprotonation. It's acting as a base. We form the alkoxide anion. Now the alkoxide anion acts as the nucleophile, and it is going to target an electrophilic carbon on a primary substrate, forcing the leaving group to leave. So notice here we have X minus, and they're writing it here as NaX. Just remember that sodium is a spectator ion, and it's just going to migrate over to the halogen's negative charge to keep it electrically balanced. So notice here we've added a methyl group. That methyl group just simply came from whatever is attached to the halogen in that primary substrate. So this is an SN2 process, the nucleophilic attack of an electrophilic carbon on the substrate. The alcohol is deprotonated to form an alkoxide ion and then acts as the nucleophile as it attacks a substrate. The substrate, because it's SN2, remember that we want a good leaving group, so oftentimes we'll use iodide as a good leaving group. And then the leaving group leaves, creating a new target where we've added a methyl, turning an alcohol into an ether. So remember, primary or methyl substrates work best for SN2. We would want the iodide leaving group to be at the end of the carbon chain to promote substitution over elimination. So this is a much more practical application. And let's kind of just really emphasize the importance of selecting a primary substrate and any type of alcohol. So if our job is to produce methyl, on one side of the oxygen I see a methyl group, on the other side I see a tert-butyl, and that name, MTBE, simply stands for methyl tert-butyl ether. How would we go about selecting the proper reagents to form this ether? Now remember, we always start with an alcohol, and we're going to treat it with sodium hydride. We want the hydride negative ion so that it can reach out and deprotonate the alcohol. When the hydride deprotonates the alcohol has to be able to reach that electrophilic carbon, dispelling, kicking out, if you will, the leaving group iodide, and that will form the ether linkage. So here's your two choices. Do we start with a tertiary alcohol and a primary substrate? That's what we see on the top arrow. A tertiary alcohol and a primary substrate. Versus a primary alcohol and a tertiary substrate. What works best for the SN2 mechanism? Remember, we generate the alkoxide anion. So in the first step, we would form methoxide, or, as we mentioned here, you'd form tert-butyl oxide, the anion from the carbon that's attached to three other carbons. So both of those are relatively easy to form. They would both be deprotonated, but then we have to be sure that the substrate can actually undergo an SN2 nucleophilic attack. How easy is this oxide ion in the methoxide? Is it able to attack a tertiary substrate, forcing the leaving group to leave? That's a very difficult substitution because of steric hindrance. This is very difficult to accomplish and actually would promote elimination. With the primary substrate, that carbon here is very open to attack, and of course this would be the favored mechanism. We want a primary substrate to react with the oxide anion. So they must be able to attack the electrophilic carbon, and that's why we want the alkyl halide to be primary and just start with any type of alcohol to produce your desired ether. So let's try some. Let's give it a whirl. Show reagents that you could use to prepare the following ether via Williamson ether synthesis. So this is our target molecule. This is what we'd like to make, and it's an ether linkage, ROR. On one side of the oxygen, we have a phenyl group. On the other side of the oxygen, we have an ethyl group. So just thinking this through, these are the choices of how to prepare the ether. We could start with this aromatic ring and make it the alcohol, and then react it with ethanol, or not ethanol, we want the iodide, we want this to be the substrate, and we want this column to be the alcohol. So one choice is to start with phenol and react it with the 2 carbon with the leaving group of iodide, ethyl iodide. Or, here's another choice. We could make the alcohol come from the ethanol group, this 2 carbon chain, and we could make the substrate the aromatic ring attached to the iodide. What would promote an SN2 reaction better? So really we just start with classifying the groups on either side of the oxygen atom and then making a decision which is the better choice of creating an SN2 substrate. And remember, the goal is we want a primary substrate. As a matter of fact, this sp2 carbon is not capable of SN2 reactions, so that we can eliminate that choice immediately simply based on the hybridization. And so thinking through our steps, we really come up with the best choice, giving the substrate, we want it to be primary, making the alcohol choice, the phenol, and then putting the pieces together. We see with the presence of a strong base, we can convert our alcohol into an ether linkage in the presence of this primary substrate. Now remember, since this hydrogen, when that alcohol is deprotonated, this goes back to a previous lesson, this negative anion has resonance, and it is much more stable than if it were not near a pi bond. And so when I put sodium hydroxide on the arrow, that's okay because it is capable of deprotonating the hydrogen that's on the phenol, since this phenol is more acidic. However, just to bring up a previous lesson, if I had cyclohexane, I cannot deprotonate that hydrogen with sodium hydroxide. That is not a strong enough base. I would have to use hydride as a strong enough base to deprotonate cyclohexanol over phenol. So careful selection of the base. This is a more acidic proton than on the cyclohexanol. So selecting the base to deprotonate the alcohol, step 1. And then step 2, using iodine as the good leaving group, I'm going to add on those 2 carbons to create my target ether. Now the good leaving group can be iodine or a tosylated oxide compound. I think it's easiest to just put the iodine on there so it's 1 step instead of 2. Let's take a peek at a next example. What reagents can we use to prepare the following ether via a Williamson ether linkage? Here I have a cyclohexane and a 1 carbon group. Here I have a 3 carbon chain, and here's the ether linkage. We want to identify what's on both sides of the oxygen. And so when I do that, I'm really giving myself choices of the alcohol and the substrate. So in one condition, we could use the cyclohexane with the methyl group here, right? This is the carbon here. And we can turn this into the alcohol, leaving the substrate to be the second position on this side of the carbon chain. That's choice 1. Or choice 2, we could make the alcohol this side of the ether linkage and making the substrate then the left side originally. And so we could place our iodine here. So these are the two choices as we begin to strategize the best approach for our Williamson ether synthesis. This is the key to making your decision. Choice number 1 gives us a secondary substrate. Choice number 2 gives us a primary substrate. And we know that SN2 substitution is favored when we have a primary substrate. So this begins our reaction then to say, let's start with 2-propanol. There we go. And our primary substrate will begin our reaction. And this time, since we have an alcohol that we have to deprotonate, we're going to need a strong base. It is not going to be resonance stabilized. And so with this, we would start with like a hydride, and a H would work in terms of deprotonating, forming the alk oxide anion, which would then attack this nucleophilic carbon, producing the desired ether. So that 2-step approach, we want to put a strong base in to deprotonate the alcohol. We want then to add the appropriate substrate. And the appropriate substrate then comes from the cyclohexane, and it had the methyl group attached. Whoops, and it jumped up, sorry. And here we would see the final answer. We decided that the secondary alcohol reacting with a primary substrate would form our ether through the Williamson synthesis. To produce a synthesis of an ether using an alkoxy mercuration demercuration would prevent any type of rearrangement from occurring. Let's review something from our past. Noticing from section 8.6, we had seen this mechanism, alkoxy mercuration demercuration, when we were in the alkene chapter, which was chapter 8. Sitting on the arrow, we see that we have an alkoxy mercury compound. Notice this mercury, and when I see that, I know that it is not a carbocation intermediate, that the mercury is serving as a placeholder, so no positive intermediate forms, therefore no possible rearrangement. And in the second step, you see that we had used sodium boron tetrahydride to actually protonate that alcohol at the last step. Notice our mechanism, it's Markovnikov. The hydrogen adds to the least substituted carbon in the first step, and then of course the alcohol would form on the carbons that are most substituted. So that is a review mechanism. Starting with an ene, we produced a Markovnikov addition to an alcohol. Well, what if instead of using water in this mechanism, where the water added an OH across the bond, what if we used instead an alcohol? So on the arrow now, instead of HOH, we have ROH, and that of course represents the alcohol. The hydrogen still adds to the carbon originally across this double bond. Here's the 2 carbons in the pi bond. The carbon that has the least substitutions receives the hydrogen, and the carbon with the most substitutions receives the OR from the alcohol, resulting in an ether linkage. Very much the same mechanism, except instead of water, we're using an alcohol. So on the arrow, step 1, we see our Hg parentheses OAC taken twice. Notice this in terms of what we want to add to the original alkene. Onto the most substituted carbon, I have to just carefully select the alcohol to make sure I'm adding the appropriate branch. Going from an sp2 hybridized carbon to the sp3 hybridized carbon, what do we want to add to that group? Make that your alcohol. And in step 2, NaBH4, same steps as above, we're just now using an alcohol. So let's try one. Identify reagents that you could use to prepare the following ether via alkoxymercuration demercuration. We know that's going to be the case because I'm starting with an alkene. So that's your clue that those are going to be the reagents necessary. So let's first locate the positions of the double bond. In this 4-carbon chain, carbon 1 and 2 were the original carbons that were in the pi bond. What did we add to the most substituted carbon? Well, right here we can clearly see we added OET. That just simply means that's going to be the alcohol that you add across with your alkoxymercuration followed by demercuration. And that's all there is to this. This reaction would have the first step of adding your reagent, Hg parentheses OAC taken twice, comma, and the alcohol we would want to add is ethanol. And then in your second step, the sodium boron tetrahydride. And we have now identified the reagents to use. On the least substituted side goes the hydrogen. So we don't see it, but that's where the hydrogen went. And on the most substituted side, we added the ether linkage of OCC. And that's really all there is to that step. Select the alcohol from the ether linkage present on the product side. Simple enough. In our last section, I'm going to make a talk about reactions of ethers, and 2 reactions are going to be explored. With these 2 reactions, we'll look first at acidic cleavage. Now we know cleavage means to break a bond. When heated, in the presence of a strong binary acid, such as HX, X representing the halogen, HI, hydroiodic, HBr, hydrobromic are good choices. HCl doesn't seem to be as efficient in this reaction, so your better choices would be the most reactive binary acids, hydroiodic and hydrobromic. When an ether undergoes acidic cleavage in the presence of a strong binary acid, so it's saying binary because it doesn't work with oxy acids. So for example, HClO3, that's an oxy acid, doesn't work. We want the binary acid to keep the oxygen absent of the reaction vessel. So here we have an ROR. We know that to be an ether. And notice it says excess amount, so this is going to be a 2-step mechanism, breaking both sides of this ether linkage 1 step at a time. So we need excess amounts of our strong acid and in the presence of heat. What we'll notice is that the first alkyl group to the left forms an alkyl halide in the first step, and in a next step, the second alkyl group forms an alkyl halide. And of course, the oxygen in the center ends up being protonated to form a water molecule. So again, I mentioned this is a 2-step process, and we can just look quickly at its mechanism. Here we have an ether linkage. And notice in this particular example, it does not have to be, but this is a same group. We have a methyl group and it's a methyl group on this side. They do not have to be symmetrical. This works for any ether. In our first step, the oxygen in the ether linkage reaches out for the proton in the binary acid. And this then, the X negative, is cleaved. So here we have the generation of X negative, that will be your bromide or your iodide. And remember, what we just did here was turn this oxygen into a better leaving group. So we protonated the ether. In our first step, the acid protonates the ether and the oxygen site. Now, the very halogen that we just generated, the halide negative ion, then acts as a nucleophile on this electrophilic carbon. And when it does so, it attaches to there, breaking the bond to form an alcohol. Now, it does not matter what side of the oxygen you start on. This particular ether example gave us two identical linkages, both to methyl groups. But if they were not identical, it does not matter which one you start with. They will both undergo the same process. This alcohol now is going to go through the same process as the original ether did up above. So the alcohol now becomes protonated. It does so by reaching out for another proton from the binary acid, HX. We protonate it to turn it into a better leaving group. This halogen, this halide negative ion, then acts as the nucleophile, reaches out for the electrophilic carbon, and the leaving group leaves. And when it does so, you formed a secondary alkyl halide. So on one side of the ether, we made an alkyl halide. On the other side of the ether, you made an alkyl halide. And eventually, right there is the production of the water molecule through the mechanism. So ROR, in the presence of a strong acid, let's say it's HBr, and it will be an excess amount simply because it's a multiple step process, not one mole, but we need multiple moles to make this work. Your product side would be RBr, R prime Br, and a water molecule. So acidic cleavage. Cleavage means to break the bonds, turning them into alkyl halides. So for example, what happens in this reaction? Here we have a benzene ring attached to an oxygen, attached to an R group. So this is an ether linkage. In an excess heat, excess HX, which is our binary acid, and in presence of heat, we form phenol and the alkyl halide. So why did this not form another alkyl halide? I wanted to emphasize this example because the secret to this is right here. This carbon attached to the ether linkage, this is where we would split, involves SN2 substitution by the X negative from the acid. We understand that this reaction, where the X negative would attack an sp2 carbon, will not occur. That SN2 must have a hybridized sp3 electrophilic carbon for it to occur. And so we only formed one alkyl halide, the Rx, and not two alkyl halides, because this reaction mechanism stops with that particular reaction. Now go back and remember, if we took off one side, we produced an alcohol, right? The original ether, removing the first substitution there, the first alkyl halide forms, leaving us an alcohol as the other product. So you'll stop with the alcohol and not the next step where you would turn it into an alkyl halide. So sp2 carbons cannot undergo the SN2 substitution. So you stop with the alcohol and then one alkyl halide. Just as a reminder that you want to check to see as you're cleaving the bonds, make sure to form the alkyl halide, it must have an sp3 hybridized carbon to do so. And let's just quickly practice. I see on the arrow excess hydrobromic acid in the presence of heat. The ether linkage is going to be cleaved if the carbons leading in are sp3. And I just want to check, and yes, both are. So that means the reaction will proceed at both sites. So we have a 3-carbon chain, and leading out is another carbon. So here is you know what? They're identical, aren't they? Both sides. This is a symmetrical ether. So that means we're going to produce 2 like products, right? We're going to produce this product. Whoops, that has to lead out to the bromine. So here's carbon 1, 2, 3. On carbon 2 is this methyl. Here now would be the bromine leading out. So 1, 2, 3 is now how I would name that. At group number 1, we have 1 bromo. At carbon number 2, we have a methyl. And the branch is 3 carbons long. So 1 bromo, 2 methyl propane. And that is going to be produced twice. How about down here in the next example from your homework? Identify the ether linkage and look to see what's on either side of the oxygen. I see a carbon here that is sp3 hybridized. So yes, this will be cleaved. Acidic cleavage can occur at an sp3 carbon. But here I notice this is an sp2 carbon, so no cleavage, no bond breaking, if you will, because of that sp2 hybridization. So even though there's excess amounts, we will only be able to cleave 1 bond right here. So on this side of the arrow, the oxygen that originally was an ether linkage will now have its alcohol functional group. And how many carbons here? 1, 2, 3 carbons there. This bond is then cleaved, so 1, 2, 3 carbons leading out to an iodine from the binary acid. So our 1, 2, 3 carbons present, we broke the bond and attached to make the alkyl halide. There, I got it. Alrighty, so that's easy enough. Let's take a peek at a next reaction called auto-oxidation. In section 10.9, this chapter 10 was all about radicals, if you recall. We saw this reaction occur. I'm just bringing it back as a reminder. Auto-oxidation, section 10.9. We learned that ethers undergo auto-oxidation in the presence of atmospheric oxygen to form hydroperoxides. So let's understand. Here is a tertiary carbon, and in the presence of molecular oxygen. Now remember, oxygen as a molecule is a double bonded, most stable octet for each of those oxygens. But as a radical, we saw oxygen redistribute its electrons to form 2 sides, each oxygen with a lone electron. So oxygen as a radical has 2 sites available for perpetuating radical mechanisms. So when you see oxygen on the arrow, think of it actually as a radical with only a single bond forming, And that single bond between the two oxygens allows one lone electron on each of those. So let's take a look at how the reaction proceeds via the radical mechanism. We see our 3 steps of any radical mechanism. The first step is always an initiation. We know that initiation has to form radicals. That's the job, to initiate. And so we'll see an alkene, such as RH, in an initiator, whatever that might be, some radical to initiate the propagation steps, is going to form a carbon radical. So hydrogen abstraction initiates this mechanism. To propagate, the propagation involves a first step of coupling. Notice this is where we see molecular oxygen as a radical. The first side reaching out to pair in a coupling reaction, forming this radical group from the oxygen, forming the ROO. Notice it's still a radical because the second site of oxygen there is still unpartnered. So in propagation, we form a new radical that then completely gets used up in the next step. So what's made in this step gets used immediately in the next step. So you make it, step 1, use it, step 2. And again, this is a hydrogen abstraction, where the result, of course, is this peroxide, ROOH. And we've regenerated the carbon radical. What I use in the first step must be regenerated in the last step so that the reaction will propagate. And now overall, the R radicals, one is used, then regenerated, they cancel because we see one on each side of the arrow. This intermediate was formed and then used, so it actually cancels from the reaction. And what's left is the actual observed equation. So in terms of, stopping in terms of a coupling, but what's left, we saw the O2 oxygen in the presence of HR, our alkane, or alkyl group, forming an ROOH as the product. And it occurred by radical mechanism. Ethers follow this same pattern. Here I have a diethyl ether in the presence of oxygen, and I want you to think of this oxygen as a radical that has 2 sides of lone electrons. And at the end, you've terminated to create a hydroperoxide. Now, this reaction occurs spontaneously, but the kinetics are very slow. It does so if you leave a jar of an ether open to the air, it will degrade to produce a peroxide. So it's a slow but spontaneous reaction. There are many lab benches that have old ethers that when you open the lid, you get a strong peroxide smell. And if you smell an old bottle and from the stockroom giving off this peroxide smell, it's a pungent odor. You now know that that ether has degraded into a hydroperoxide, and therefore you know not to use it because it's a very violent, very explosive reaction. So ethers have a shelf life. This reaction I've shared with you is not one we desire to have happen. It happens over time as ethers age. They tend to degrade just in the presence of oxygen. So again, it's very critical to make sure the ether jars are sealed tightly to prevent this reaction from happening. It is not a desired reaction. And the last comment I want to make is about a cyclic ether. Cyclic ethers are one that contain an oxygen as a member of a cyclic structure. Here I notice that an oxyrane is a 3-membered ring. Whoops, I can spell. 3 members. 2 of those members are carbons, and the third is the oxygen, or a 3-membered ring. Here I see a 4-membered ring. Oxytane is a 4-membered ring. 3 of them are carbons, 1 is oxygen. Oxolane is a 5-membered ring. 4 are carbons, the 5th is an oxygen. And an oxane ring system is a 6-membered ring. 5 of them are carbon, and the 6th is an oxygen. Of these cyclic ethers, I'd like us to know the 3-membered ring, oxyrane ring system, simply because it's the most reactive of these cyclic ethers, and the explanation there very quickly is simply based on ring strain. It's a very tight, very small ring, therefore we know the smaller the bond angles, the more strain there is on that particular cyclic structure, making them very highly reactive. These 3-membered ring systems can have substitutions on them. So if we have a 3-membered ring from up above, and you can see carbon 1, carbon 2, and then the oxygen is the 3rd member of the ring, you can see at those 2 positions of carbon, you can have up to 2 substitutions each, making a total of 4 possible. And the reason I mention all of this is because we need to know this word as a critical intermediate for many of our reactions. A substituted oxyrane is known as an epoxide. An epoxide, and I'll share with you where we've seen this before as I slide down the screen here. And in terms of nomenclature, the nomenclature for an epoxy group, an epoxide, is now going to be named as a functional group epoxy. Find the longest carbon chain that contains this linkage, and in this made-up example, I can see that the carbon chain 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, so either direction would have found 5 members, gets the base name pentane. Between carbon 2 and carbon 3, I see the epoxy linkage. And on carbon 3, I see an ethyl group. And on carbon 2, I see a methyl group. And it's just all alphabetized. So I have 3 ethyl, 2 methyl. That is alphabetized. Notice this 2,3 epoxy is part of the root word name, so it's listed right in front of the pentane. But it is listed as a linkage between carbon 2 and 3. So attach it directly to the last name. Now, where have we seen these before? We did this when we looked at a dihydroxylation reaction back from chapter 8. When an epoxide is subjected to an attack by a strong base, such as sodium hydroxide, ring opening occurs to create a diol. Notice that this 2-carbon ring has been opened up. Here's your 2 carbons, but on either side now is a hydroxyl group. So in the presence of a strong base, the ring opens and forms 2 hydroxyl groups. This reaction was explored in section 10 of chapter 8. Taking an alkene and treating it with a peroxy acid created an epoxide intermediate. Now we have a better idea of what an epoxide is. It's a cyclic ether. The acid then breaks the ring apart and protonates to create a diol, and this was very stereoselective. We saw that it was a trans diol, so you would have enantiomers form in this cyclopentane group. Cyclopentane diol in the trans position was the yield when we started with cyclopentene. And we're just emphasizing that this went through a cyclic ether intermediate, now known as an epoxide. In the presence of the acid, we open the ring up and create two hydroxyl groups in the trans position. And that, my friends, is the end of our lesson, the end of the lesson for ethers, and the end of our final new topics in semester 1. Congratulations. I look forward to seeing you in class.